Hi, this is Math Kimchi, and today we will be looking at a Connect 4 program that I made, which includes an AI, and the AI uses Minimax and can also use Monte Carlo as a way of scoring the leaf nodes. So right now I started the game, and currently it's person versus computer, as you can see here. The way you can change that is by changing these two things. So if I make this C instead of P, then it will be computer versus computer. And if I make this the first two elements P and P, then it will be person versus person. But right now it's set to person versus computer. And if you look in the code, you will notice that instead of using player 2 as what would be player 2, I use player -1, which makes some of the calculations easier. The third element in this list is the difficulty, and all that does for now is if you set it to E, it allows you to undo your moves, and I'll show that later. And the next thing you can see here is what says that max def equals 4, and also the scorer. So the max def is for the Minimax part of the AI. It means that the Minimax will think 4 moves ahead, but actually it means it'll move 3 moves ahead. That's because the actual max def is 1 less than the max def in here. You can only do a max def of an even number, or at least this max def of an even number, so an actual max def of an odd number, and that's because if it's an odd number, or if the fake max def is an odd number, then it just doesn't work well for some reason. I'm working on fixing that, so anyways, the next thing is the scorer, which in this case is equal to 15, and what that means is that for every leaf node, the Monte Carlo will simulate 15 random games. So now let's look at the actual game. It asks you to place a slot from 0 to 6. The reason why it's 0 to 6 is because computers count from 0, which makes things easier to work with. And let's just do 3. And it'll think for a while. And it did a 3. Now you might notice that it printed a game log. Right now the game log is 3 and 3 because I placed a 3 and then it placed a 3. So this is the first move, the second move. If something was here, it would be the third, fourth, and fifth, and what this is what the game thinks will happen. So this is right before it played a 3. So when this was made, the game log was only 3, and you can see it predicted 3 moves ahead. And what I mean when I say what it thinks will happen is what it thinks will happen assuming both players play the best moves, and that implies that it thought 3 was the best move for it. And that's what it told the Connect 4 game, and the Connect 4 game took that and played a 3 for the AI. And this is the score. And the score gets bigger the more advantageous the computer is, and it becomes smaller the more advantageous the player is. So right now it seems like the player has an advantage. So let's just play 3 again. You do have to wait for a while if you make this 4 and 15. I recommend the max depth of 2 and a scorer of 100. That's pretty fast, and it's also not that dumb. Or you can make it like 2 and 150, which is also pretty fast. It played a 4, and now it's saying that it has an advantage. So now that we looked at how the game works, let's look at the actual code. The first 2 things on my code are comments, and the first comment says that the AI only works with even max depth, not with even actual depth. It only works with odd actual max depth, and I'm still working on fixing that, so that's going to change later. And the second comment is to ignore things like evolving equals false and all the classes at the bottom, as I am also working on them. So by that I mean this, and also this, and everything under the 4 main classes. So everything under these 4 classes, well, and also this, you should ignore. So it's these 2 classes. I'm still working on them. So if you want to use my code, I recommend that you delete this line and these lines and everything here. And after that, it imports random, and random allows you to choose random integers, and that's useful for Monte Carlo because Monte Carlo simulates random games. And then we have types. What that does is, if we run Python, let's make a equals 1. So a is an integer, and b equal to 1, 2, 3. So b is a list, and c is a function. But what type does it returns whatever it is in here is. So since a is an integer, it returns class int. And int is short for integer, and type b will return a list because b is a list, and type c will return a function. And this is useful because you can do something like type a is equal to a list in order to find out if a is a list, and it will say false. But if you go like a is equal to int, then it will be true because a is an integer. And that also works with b. So if I go like type b equals list, it will say true, and type b equals int, it will say false. Now, if we were to go like type c equals int or list, it will obviously say false. But we can't do type c equals function because we will get an error. And you can't do something like type a equals function is equal to function either, because a function is not defined. So instead, what you have to do is you have to first import types, and then you have to go type C is equal to types dot function dot no dot, and then function type. So if you do type C is equal to types dot function type, where F and T are capitalized, then I'll say true. And you can also do this with A and also B, and it'll say false because, oops, I don't know what that is. Yeah, so that will result in a false, but it still works. And I'm not sure what I just did. Oh, I think I did insert. Is that left click? Oh, well, I'm not sure why that did that, but anyways, types is useful to do something like type something is equal to function, but you have to change this to types dot function type. Anyways, the next 4 lines are a scoring system that doesn't matter if we are doing Monte Carlo, so I won't really explain it, since we're just going to pretend like Monte Carlo is the only scoring system that we use. So I also won't explain the class Connect 4 either, because I wrote a lot of comments explaining it. So if you're going to make your own Connect 4 class or something, then I recommend looking at the description, and I will put this code in the description so you can look at the comments. But I will explain that the play function, because this is where Minimax is called. So this is where Minimax is called. First, it'll do equals Minimax, and it will tell it a bunch of things, and then it will say thing equals dot return best. And what thing is this thing? So it's the predicted game log and also the score. And that's basically it for the Connect 4 class, but yeah, basically what the Connect 4 class does is it's where the actual game happens and the actual AI happens in here. I also won't go into too much depth with the Minimax class, because it's pretty similar to the Minimax for the tic-tac-toe, but I guess I'll go over most of the differences. So one of the differences is that instead of making a win just a really big number, well, I'm pretty sure at the tic-tac-toe game, I just made a win a 1 or -1 and a tie a 0, because it looked at the full depth. It could look at the full depth, but for this one, originally I made it so that a win would be equal to 2 to the power of 30. This is what power of means. So instead of doing this, you have to do this for some reason. But that's not the only difference. You also add, well, you technically subtract self.fitness, but And what I mean by self.fitness is, the score, and that's also what I mean by self.Monte Carlo, and then self.scorer. Wait, what? But anyways, the reason why it does this is because if I don't do this, then it'll just give up when it realizes that it has no way of winning. But this makes it so that even when it knows that it is going to lose, it still chooses the move that results in the highest score. And the reason why there are like two versions of this is because this activates when this is used when this is true. When this is true, and what this is, or at least what this does, is it checks if the scorer is a number, or if the scorer is a function, I guess. Because if a scorer is a function, then it'll be scoring a different way than Monte Carlo, and I won't really go into what it does, but for now, just ignore this. Think it was just this, and yeah, this is what happens when there's a win, and when there's a tie, then it does the same thing as the tic-tac-toe. It just returns 0 along with the game log that it thinks will happen. And this is not on the tic-tac-toe game, because in the tic-tac-toe game we just calculated everything to the full, but in this case we can't do that with Connect 4, because Connect 4 has just way too many games for that to happen. At least with this code. I'm pretty sure someone did solve Connect 4, but we won't be doing that in this code, and we won't be doing that in this code, but what this does is, if maximum depth is reached, then it will just return the score. And I'm pretty sure all of these are the same, and these are obviously different because the winning and tying in Connect 4 is different from tic-tac-toe, but this is the same as this and this, and it doesn't really matter. What tie check does is it just checks if the game log has a certain amount of players, or if there have been the width times height amount of moves done, which will mean that everyone would have, or every square would have been filled, and that it's a tie, assuming there isn't a win. And what win check does is, I'm pretty sure this checks it just checks all the possible Connect 4s, and if any of those are all filled with one type of players, or one player's token, or I'm not sure what I should call that, but I think I know what you guys mean. I think you know what I mean. So it just checks every possible Connect 4, and for all of them it checks if a Connect 4 has actually been made. And return min or max just returns takes in a list, and from that list it just either gives a minimum of the list or a maximum of the list, depending on what the depth is, I'm pretty sure. And yeah. Make move just does the move, and LM Finder finds all of the legal moves. And fitness is one way of finding the score, but the other way is Monte Carlo. And I'm not sure why I do this. I'm pretty sure I can just replace games amount with self.scorer, but I don't know. I might break something by changing that, so I'm not going to right now. But that was basically Minimax. That was Minimax. It's basically the same as Tic-Tac-Toe, but it's better. But it has a lot more features to it. Now that we went over the class Minimax, let's look at the class MC and Monte Carlo game. So the class MC, which stands for Monte Carlo, is called in the function Monte Carlo of the class Minimax. And the function Monte Carlo returns whatever return win percent returns. And so let's look at the class Minimax. These 5 variables in MC isn't too special. It's in basically all the other ones. But self.games amount is the amount of games per leaf node. So in this case, self.games amount will be 15, and self.games is just a bunch of, it's a list of the game board of the leaf node that called MC. And self.sum is originally set to 0, and return win percent returns self.sum. So what return win percent does is, for every game board in self.games, it runs a random game, and mcg.returnResult will return either 1 or 0 or -1. It returns -1 when the negative first player wins. It returns 0 when there is a tie, and it returns 1 if the first player wins. And that is added to self.sum, so whenever there's a tie, nothing happens to self.sum, but if 1 wins, it gets bigger. If -1 wins, then self.sum gets smaller. So now what Monte Carlo game does is it simulates one random game, and returns the result of it. So first, the init function of Monte Carlo game has nothing special. All of these variables are in the other classes, so I won't go over that. Return result is actually pretty similar to return best of class Minimax. So what it does is it first checks for a win, and then it checks for a tie, and that is exactly what return best of Minimax does. And when there is a win, it returns the negative of self.player. And I wrote here that I'm not sure why it has to be negative. I think it is because it checks for a win and also a tie after the player has been switched, but I'm not really sure. And with self.makeRandomMove, it just comes up with a random move and makes one, and then it just does return result, and then it just does class, and then it just does a recursion thing and calls itself, and then you return, you just return the return result of temporary. Now, make random move first asks for all the legal moves from LM Finder, and that's going to be a list like 1, 5, and 6 or something, and out of those it chooses a random one, and this is the code that chooses a random element from a list. Random.randint comes up with a random integer in between this and this, and it is inclusive, meaning that in this case 0 can be picked, and also len lm -1 can also be picked. And the way that random.randint works is len lm, it just finds how many elements there are in lm, and we have to subtract that number by 1 because len lm counts from 1, even though most things in Python counts from 0, and that's why we have to take out 1, because it will be bigger. And what this does is it just chooses it chooses this element of the list LM, and if this is 0, then it will choose 1, and if this is 1, it will choose the second element, and if this is 2, it will choose the third element of LM, and so on. I'm not sure why make random move returns self.makeMove. Oh, so make move doesn't actually change the self.state. I'm pretty sure it just changes a copy of self.state. That's not really important, but yeah, make move, it just creates a copy of temp state, so basically make move just creates a copy of self.state. So this is what that is, and it changes the game log, and then it finds like an empty space, and it changes the lowest empty space in the column of a duplicate of self.state, and it returns that. So yeah, that's basically it.